Hi, we're continuing our discussion about column design. We went over the basics in the previous lecture. This time, we're just going to talk about what is the pure axial capacity of column design of columns. And this is based on the University of Illinois tests that uh, resulted in what's called the column axial addition law. The University of Illinois has a long storied history of excellence in reinforced concrete, prestressed concrete design. For example, we talked about Danny Kuchma and the effect on the new size effect things. Um, these tests. And you might not know, but a past department head here, Art Barisi, used to be the department head at University of Illinois. And also my buddy in Japan that I hang out with and we do work together. We started out as PhD students together at University of Washington, but he went on to get his PhD from the University of Illinois. Anyway, this work I'm going to talk about comes out of the University of Illinois. The column axial addition law is for pure axial load, meaning moment is zero or E is zero, that eccentricity. And they say you could just add the concrete and the steel strengths. That's why it's called the axial addition law. Just add the strength. So 0.85 F prime C times the area of concrete. And what you need to do is take out the area of concrete missing because of the holes from the steel bars going in there, and Fy times the area of steel. Now, the area of concrete is the gross area, so if it's like a rectangle, B times H, minus the area of steel, because wherever there's steel, you can imagine there's no concrete, so it'll be like holes in the concrete. And so it's 0.85 F prime C times the gross area minus the area of steel plus Fy times the area of steel. And if you just collect the area of steel terms, you get that equation on the bottom. 0.85 F prime C times the gross area, B times H, plus Fy minus 0.85 F prime C times the area of steel. And this will give you the pure axial strength of the column. Okay, so if the load was going straight down the middle of the column with no eccentricity. Well, is that possible? Is it possible to have zero moment? And the answer is no. And what that means is that there is a little bit of moment no matter what. And what we're going to do, instead of figuring out what the minimum eccentricity is, you can imagine that when you add moment to the axial load, it reduces the strength. And so if moment is zero, you get your peak axial strength. And once you add moment in there, the axial strength will decrease. And so instead of a minimum E, what we're going to do is reduce the maximum axial load. What we're going to do is for tied columns, we'll take 20% off the top, okay, so 0.8 PN0. And for spiral columns which perform better, we're going to take 15% off the top, or 0.85 PN0. This 0.8 and 0.85 are not the phi factors. You remember those were 0.75 and 0.6. For example, the phi factor for tied, if you remember, was 0.65. And so if you take 0.65 for phi, and then you reduce that by 0.8, that's 0.52. You can only get half of that Illinois addition law strength in your column. Here's an example. So it's 0.85 F prime C times area gross plus Fy minus 0.85 prime C area steel. For number 9 bars, F prime C is 3.5, 12 by 12, 144 square inches. And for number 9 bars are 4 square inches. And so here you get 660 kips. But again, you would have to take 52% of that as your maximum allowable axial strength. The last thing I want to do is talk about confinement. And the reason I want to talk about confinement is that when you look at the behavior of columns in an earthquake, look at this picture in the middle, B, the ties. Typically in an earthquake, what immediately happens is the concrete outside of the tie, it just comes off, it spalls off. It's like that concrete isn't even there. It does not do anything structurally once there's any sort of lateral movement. It just comes off. You can't count on it. But we just took 0.85 F prime C times the whole area, not the area times the core concrete. We took 0.85 F prime C times the whole area, and I just told you that outer concrete outside of the tie will immediately come off. Well, why does that work? And what happens is that the concrete inside of the ties is stronger than you think because of confinement. And maybe one day we'll talk about. Remind me to tell you about the Mander model that will tell us how strong the concrete inside those ties are. But for now, all you need to know is that when you confine concrete, it gets stronger. And if you took 3210 CE materials from me, we talked about this, how you get significant increase in compressive strength if you confine it. And an example is that F prime C goes up by an additional 4 times that confinement stress. For example, if you confine the concrete at 20% of the F prime C, you double the compressive strength. And what happens, the reason the Illinois Axial Law works, and it's a little bit of a coincidence, and it was quite a bit of work to come up with that Axial Addition Law, is that this concrete inside the tie is confined, because when you load the column, it's wanting to expand, and it pushes against the tie, and that tie confines the core concrete, and that confinement increases the strength. So instead of 4,000, you might have 8,000 psi strength on the inside confined. And that additional strength inside offsets the amount of area you lose on the outside. So let's say you lose 40% of the concrete spalling off outside the tie. The concrete inside the ties, not so coincidentally, increases 40% in strength. And so it's a wash. You lose 40% area, but you increase the strength by 40%. Now, it's not a coincidence, because what they did in the Illinois tests was they came up with how far apart you need to put these ties, or how closely you need to space them, to guarantee that you would get an increase in strength that would offset the loss of area. And following those rules was convenient, because then you could just use the gross area. Now, while that worked, what we didn't think about until maybe early to mid 70s was that after the concrete spalls off on the outside, those bars, the bars in the corner, they're like little miniature columns, and they're not very big. They could be like a number 11 bar, and about that big around, maybe that big around. And with the spacing from the Illinois equations, they were far enough that those bars could buckle. And so the current spacing recommendations for columns, which we'll get into later, take that into account. But unfortunately, we didn't realize this till, I'm oversimplifying it, but we didn't really realize this to mid 70s. And so things built before about 1973, they don't have enough stirrups hoops going around, and so we need to retrofit those to stop the bars from buckling when the cover comes off. But anyway, that's confinement and the axial addition law. And so this is how you calculate the pure axial strength. And remember, that gets reduced. For example, a tie gets reduced by a phi of 0.65 and the additional minimum eccentricity reduction of 0.8. And but anyway, the real fun for this comes when there is moment and axial load, and that's the real discussions we'll have next, and the little bit complex calculations, and we'll introduce a concept called interaction diagrams, but that's for next time.